First we should finish our breakfast, but then we should get on to the physics.
Yeah, I agree. I've got strawberries for breakfast.
Strawberries too. Strawberries are good.
Do you know what's the best thing about strawberries, though?
Well, you have 5 a day.
It's not quite what I was thinking.
No, they're red.
Well, no, it's not that.
That's pretty cool.
No, it's this free bit of bubble wrap. I don't know why, but I really like it.
I don't like bubble wrap. Oh, it's Christmas soon. Get loads of bubble wrap.
Oh, that means I'm going to get loads of strawberries.
I love strawberries.
Anyway, we should get on with the physics.
We should get on with physics, yeah.
Enough about our breakfast. How are you?
I'm good, thanks.
Was I talking to you?
Hiya.
So, momentum. You've probably heard of it before.
Yeah, it's quite momentous.
And for a moment, we're going to talk about it.
Huh.
So, firstly, what's the equation for momentum? I think it's a good starting place.
It's mv, mass times velocity, but what stands for momentum?
It's easy, it's going to be an m for momentum.
No.
No?
No.
Oh, because mass is...
Yeah, so it's...
LM, linear momentum.
No, it's not either.
Phi, rho,
No.
Z.
Z? What would Z be?
Zodiac momentum.
Sounds good, but it's not that.
No?
No, you ready?
I'm ready.
I'll blow your mind. It's P.
P? But why?
No, P.
Okay.
So this equation comes often with our favourite equation from AS, which is kinetic energy.
Which is a half mv squared. Now, I mentioned linear momentum. The reason I'm mentioning that is there is a thing called angular momentum, which we'll do later in your A2 physics course. For now, linear, it's straight lines. If you spear tackle a train horizontally, you'll probably die.
So don't do that.
No.
Life advice. I think the best way to explain the relationships about mv and the other equations, because it isn't the only one for momentum, is go for a question.
Now, I have got a little question for you, but word of warning, it's probably best to do it in a table. There's quite a lot of information.
Oh, okay, alright.
So I'm taking a worked example from the book. I can't take all the credit. I'll take most of it though.
Yeah.
So, a truck is going north along a motorway.
You just have that a truck.
Now, it has a mass, that's something that's going to be taken into account, of 4,000 kilograms.
That's quite a lot.
Well, trucks are pretty heavy.
Yeah.
And then a velocity is another column there.
Okay.
18 metres per second. That's not that quick, but then trucks don't go that quick. Then there's a car, that's the other thing you're comparing it to, also going north, so they're going in the same direction.
Cool.
Has a mass of 1,400 kilograms, so you'll notice it's much lighter than the truck, which is realistic, with a velocity of 35 metres per second, so it's going quicker, which again is realistic on a motorway going north. Why would they be going north though?
There's not much up there really.
Might be going to visit Hagrid, I guess.
Oh, I like Hagrid.
And that's all it gives you, but then it asks you to calculate some things. So in the calculator you're going to have more rows here. So the first one, kinetic energy of each of the vehicles.
Okay, so I'll put in another table, so we can fill it.
Yep. So kinetic energy, we can use this half mv squared, and in fact that's what you will be using because you only have mass and velocity so far. You won't be using any of the other equations for kinetic energy.
Absolutely. So, put these numbers into our equations. A half of 4,000 is 2,000 times 18 squared.
We're going to need a calculator.
You are going to need a calculator.
Do you have one?
I do.
Yeah? Do you want to go get that?
I will, alright, I'll just try and quantum jump to it.
Okay.
Down the walk.
Alright, I'll keep them entertained. So guys, what part of a fish weighs the most? That's right, it's the scales. It's a good joke, isn't it? Can't take all credit for that either. Part of it comes from www.funnyjokes@notsofunnyanymore.com.org.net.gov.uk. So you're back.
Yeah, I'm good, yeah. I've got the calculator.
Good, can we do a half mv squared for the truck then please? A half of 4,000 times 18 squared. I would do it in my head, but I don't want to show you up.
Fair enough. It's quite a lot. Okay, I'll get a blue pen. Good plan. It's 648,000.
648,000. That's a common, not a decimal place.
Yep.
Could you do the same for the car, please?
I could.
A half of 1,400 times 35 squared.
That's a bit more. 857,500. 500.
It took me a second to realise. So, out of the truck and the car's got more kinetic energy. Despite weighing less, because its velocity is squared. Yeah, it's going quicker. Next, it's going to ask you probably to calculate momentum. I'm a genius. Calculate the momentum of each vehicle.
Right.
And that's just mv, and it's been done in red.
Ooh. It's gone forever now.
So, 4,000 times 18, please.
And that is 72,000.
And for the car, please, 1,400 times 35.
I like them on countdown. 49,000.
I put a 5, that's not in there. So, with momentum, the truck has more momentum despite the car having more kinetic energy, and these are all useful things.
There are useful things.
There's 2 more parts.
Okay.
On the page again. I told the audience my favourite joke, a short one.
Yeah, was it good?
They laughed a lot.
Oh, how do you know?
Oh, because I know. I'm a funny guy.
Oh, wow, alright.
So, see, the distance each vehicle takes to stop against a retarding force of 7,000 newtons. Now, this is where things get a little bit more tricky.
Yeah. It's a new word which isn't in AS physics, so that's the retarding force, and that means a force slowing something down against itself. So it'd be a force going south.
And you need to know that the kinetic energy, although it equals this as well, it can also equal FD, force times distance.
Yeah.
So now if we have a retarding force, we know the kinetic energy of each thing, we can now work out the distance it will take to stop it if it's got this same braking force.
Yeah. So force is this 7,000.
Yeah, so you're going to have to rearrange it to get distance. So it's going to be kinetic energy over force equals your distance. So if you could do them for the truck and the other thing, please.
First I'll do it for the truck. So that is...
The truck is 648,000 divided by the 7,000, which is the braking force on the truck. It will take...
Which is 92.5.
92.5 metres to stop the truck, sorry. Now for the car, kinetic energy, 857,500, much higher number, divided by the same number, is going to give a greater distance.
It is much greater distance. 1,225.
1,225 metres.
Okay.
Okay.
It's actually 122.5.
That's okay, just put a little dot there for me. And the last bit is the time each vehicle takes to stop against the same retarding force.
This is where we see another one of our equations, this time to do with momentum.
Yes. So, this new equation again for momentum. Momentum equals Ft as well as this. This is why all of this is useful. You can see the relationships. So if momentum equals Ft,
we know
our F. So we've got to rearrange it in much the same way, but now we're getting time. I'll bring the column back up here, so time, truck, car.
Is 10.28.
10.28 and car.
7.
7. So overall, the car has more kinetic energy, the truck has more momentum. The car takes longer to stop, but the truck takes more time.
So the car goes a lot further, but does it much quicker.
And that's probably because it was quicker to start with, isn't it? You think about what's going on, but then all these relationships can get pulled together mathematically.
They can, 'cause you're often asked to work out the change in kinetic energy or momentum.
So to do change, you're going to do the final minus the initial.
Yeah, and remember from our Subat equations in AS, that involves our initial and final velocities, u and v.
Yep. So what we end up with, if you rub this out, is we know, we'll put back up the 2 equations we did during this. You've got kinetic energy also equaling
Fd.
force times distance, and momentum also equals force times time. But if we're working it, the change in each of these things, then you can say that Ft, if we're working with momentum, equals, and as Triv said, you're going to have to bring in your Subat, you're going to have the final velocity minus the initial, that's the change in this momentum, just like that.
Yeah.
Then you can do the same thing for the change in kinetic energy. Fd is going to equal half mv squared minus a half mu squared. And these are all new equations that I thought were best demonstrated with this example.
Yeah, and they come up quite a lot. This isn't very mark heavy stuff, it's often with things.
Yeah.
They'll mix up the angular momentum with the linear momentum questions and put them into one. So we should really get on to something like that.
First I'm going to finish my breakfast.
Here's a go, dear. Strawberries are good.
We'll see you at the next video.
Yeah.